Welcome to the 8th lecture of module 4. In this module, we are discussing reactor design. Before going to this lecture, let us have brief recap on our previous lecture. In our previous lecture, we have mainly considered introduction to multiple reactions, and then we have considered quantitative discussion of product distribution for parallel reaction and quantitative treatment of product distribution for parallel reactions, and we have seen how to optimize the product distribution by different ways of contacting the reactants. In this lecture, we will start with multiple reactions, and since we have discussed in the last lecture parallel reaction, here we will introduce to the multiple reaction in series. The brief lecture outline: irreversible first order reaction in series, and under which we will consider qualitative discussion of product distribution, then quantitative treatment of the product distribution, then we will do the quantitative treatment for two different categories. One is PFR or batch reactor, and secondly the quantitative treatment for the mixed flow reactor, and finally we will cover first order followed by zero order reaction and zero order followed by first order reactions. So, let us start with irreversible first order reaction in series. So, if we consider the reaction of A, it is forming R to S, the rate constant values for the first reaction is K1, for the second reaction is K2, and if we write the rate of reactions for each step or for each species, we can write RA is equal to minus K1 CA, RR is equal to, so R is produced from A, so it is formation of R is K1 CA minus R is dissociating to S, so it is K2 CR, and for S, RS is K2 into CR, and assume that this reaction takes place when in presence of light. So, reaction takes place in presence of light. So, as soon as we put off the light, their reaction will not occur. We can treat the product distribution in two ways. One, we can take a CSTR and it is starred, and we have a light source so light will fall and we have reaction will start. So, our reaction is A to R to S. Now, how this product distribution will change? As soon as the light will fall, the concentration of A will decrease. So, reaction will start. So, if we plot the distribution of the product or the concentration change, versus the time. So, time for the exposure of the light to this reactants or to this content. So, A will react and or dissociate and form product R. So, the concentration of A gradually changes starting from a certain value. So, this is Ca naught. So, this is change in concentration of A. Now, as soon as A formed R, so the concentration of R will increase, and then after a certain time, when the concentration of A is low, the formation of R would be low. So, R will decrease. So, this is the profile for R, and as the initial concentration of R was low, the formation of S was also low. So, S will start like this and it will slowly increase depending on the presence of R. So, this is the concentration profile for R. This is the concentration profile for S. So, during this time of exposure of the light to this reactant content, the concentration profile change for all species A, R and S would look like this. Now, if we treat this system in a different way, we take a CSTR and then the content of the reactant is taken out and it is pumped through another cell where the light is put on. So, light source is over here and then it is recycled back to this. So, if we plot the concentration profile for this, we can see this is C and time. So, this exposure time to this light is such that all the reactant which is passed through this cell is completely converted to R. So, the reactant content which are pumped through this cell and the time of exposure in is such that the all the reactant is converted to the final product S. So, in this time of exposure, A is converted to R and then R is converted to S. So, this the product which is returned to this content is only S, and all the time A and S is returned and A is converted to S. So, the product concentration of S will increase, concentration of A will decrease, and what we will find, the concentration over here. So, Ca will start from Ca naught and it will come down. So, this is the variation of A, and then S will increase. So, this is the formation of S, and with 0 or very negligible formation of presence of R. So, this is R. That means, the way we contact, we can control the formation of the intermediate. So, intermediate formation we can control by different way of reacting the initial reactants. Now, let us do the quantitative treatment of product distribution, and we will first consider batch reactor. This is unimolecular type of reactions, the first order reaction in series. So, A to R to S, rate constant is K1 and K2. So, assumptions here is C R naught is equal to 0, C S not equal to 0. So, we can use the space time and the reaction time, we can use interchangeably for the batch reactor and PFR. So, we can write for the first reaction A to R, we can write Ca by Ca naught is equal to e to the power minus K1 tau. For the intermediate product R, we can write Cr by Ca naught would be equal to K1 by K2 minus K1 e to the power minus K1 tau minus e to the power minus K2 tau. And for the final product S, we can obtain Cs is equal to Ca naught minus Ca minus Cr. So, if we substitute here, Ca from this would be Ca naught minus Ca naught e to the power minus K1 tau minus K1 by K2 minus K1 e to the power minus K1 tau minus e to the power minus K2 tau. We can maximize the concentration of the intermediate as we did before. So, we differentiate the equation Cr by Ca naught Cr by Ca naught is equal to K1 by K2 minus K1 e to the power minus K1 tau minus e to the power minus K2 tau. So, if we differentiate this and set it to 0, dCr d tau is equal to 0, we would obtain tau p is equal to optimum tau p 1 by k log mean, which is equal to ln k2 by k1 divided by k2 minus k1. So, this we have already done while doing the single reaction for PFR in our analysis of the kinetic data for batch reactor or PFR. Now, if we substitute this optimum tau in this relation, then we would obtain Cr max by Ca naught would be equal to K1 by K2 to the power K2 divided by K1 K2 minus K1. Now, this can be seen, the product distribution can be seen graphically for a plug flow reactor. If we look into the Levensfield plot, over here the concentration ratio C by Ca naught. So, concentration of each species versus K1 tau is plotted over here at different K2 by K1 ratio, and you can see that the product. So, this is for A to R to S, this is K1, this is K2, and Cr naught is equal to Cs naught is equal to 0. So, this is, you can see how the Cr by Ca naught can be varied, can be changed with respect to K2 by K1. So, if we change K2 by K1 from say 1 to above 1, so then the ratio, the Cr variations would be small, and for K2 by K1 is equal to 0. So, this is the curve for K2 by K1 is equal to 0. Now, the time dependent plot is shown over here, and you can see the relative product distribution for a particular conversion. So, you can see for K2 by K1 is equal to 1, this is the 45-degree diagonal, and from here this is the product distribution, this is Cr by Ca naught, this one, and this is from diagonal to this distance is Cs by Ca naught and Ca by Ca naught. So, this is at particular conversion how the product distribution we can get for a plug flow reactor where the reaction is happening in a series reaction. Now, let us look into the mixed flow reactor. In a mixed flow reactor, let us develop the concentration time curve, and we start with no reactant or product presents, no intermediates or product present. That means Cr naught is equal to Cs naught is equal to 0. Now, if we do the material balance at steady state, input would be equal to output plus disappearance due to the reaction. So, for reactant A, we can write Fa naught would be Fa plus minus Ra into V, or we can write volumetric flow rate into Ca naught plus V into Ca plus, for first order reaction, A to R to S, K1 and K2 is the rate constant for the series reaction. So, for first order reaction, this would be K1 Ca into V. So, now we know that V by V volumetric flow rate is equal to tau m is equal to T bar. So, if we rearrange this relation, this would be V Ca naught is equal to Ca naught into V volumetric flow rate plus K1 into V. So, we can write from here V Ca naught would be equal to Ca naught Ca into V volumetric flow rate plus K1 into V. So, from here we can write Ca by Ca naught is equal to V volumetric flow rate by V plus K1 into V, volumetric flow rate plus K1 into volume. So, now this we can rearrange. This would be equal to 1 by 1 plus K1 V by volumetric flow rate. So, then this we can write Ca by Ca naught is equal to 1 by 1 plus K1, and this V by volumetric flow rate is tau m. So, we can put tau m. Now, if we do the material balance for R, component R, we can write V volumetric flow rate into Cr naught is equal to volumetric flow rate into Cr plus minus Ra into V. or we can write CR naught is 0 at the as we have assumed. So, 0 is equal to V CR plus minus K1 CA plus K2 CR. This is the rate for the component R into V. So, now if we use this CA by CA naught is equal to 1 by 1 plus K1 tau m. If we use this and if we simplify this, this would be CR by CA naught would be equal to K1 tau m divided by 1 plus K1 tau m into 1 plus K2 tau m. Now, we have calculated CA concentration profile for A and concentration profile for R. Now, we have to find out the concentration profile for S. Either we do the material balance or we can do by simply noting that the total concentration remains constant. So, simply at any time CA plus CR plus CS would be CA naught, which is constant. So, from this if we substitute CA and CR, we can get CS is equal to CS by CA naught is equal to K1 K2 tau m square divided by 1 plus K1 tau m into 1 plus K2 tau m. So, we obtained the 3 concentration profiles for the 3 components which are in series. Now, we can optimize the intermediate by differentiating the equation for CR by CA naught, this equation concentration profile, and we put dCr by d tau m equal to 0. So, if we do so, we would obtain CR CA naught is equal to K1 tau m divided by 1 plus K1 tau m into 1 plus K2 tau m. So, we can differentiate, it would be dCr by d tau m is equal to 0, which is equal to CA naught K1 into 1 plus K1 tau m into 1 plus K2 tau m minus CA naught K1 tau m into K1 1 plus K2 tau m plus 1 plus K1 tau m into K2 divided by 1 plus K1 tau m into 1 plus K1 tau m square into 1 plus K2 tau m square. And if we simplify this, we would obtain tau m optimum would be equal to 1 by root over K1 K2. And then if we substitute this in this relation tau m, then we would obtain CR max divided by CA naught would be equal to 1 by root over K2 by K1 plus 1 whole square. So, the typical concentration profile can be seen in the Levenspiel plot, where the with variation of K2 by K1 with respect to the product distribution and time can be seen over here in this case, and the relative concentration for mixed flow reactor for a series reaction can be seen at different K2 by K1 values at a different conversion level. Now, if you consider quantitative treatment of the product distribution for PFR and MFR, if we compare among these two, we can see from the Levenspiel plot that the ratio fractional yield phi of R by R plus S, or which is equal to phi R by A and CR by CA naught minus CA versus conversion plot over here. This plot clearly shows that the fractional yield R is always higher for PFR than MFR. So, the dotted line is dotted line shown over here are for the mixed flow reactor, and the solid line is for the plug flow reactor. And at any point, if we consider for this, for K2 by K1 is equal to 1. So, for any say 0.8, if we consider the conversion level for this, the conversion level for MFR is lower. The second thing is that if K2 by K1 is much smaller, as we can see K2 by K1 is small in this case, or smaller means it is smaller than unity, designed for a high conversion. So, for high conversion is better compared to the low conversion. If K2 by K1 is greater than unity, the fractional yield drops sharply. So, which is the case for K2 by K1 is 10. So, in this case the yield, fractional yield drops sharply in this region with a very small change in conversion. So, we need to design for a small conversion, but at the same time it would be helpful if we want to avoid the undesired product S, design for small conversion of A per pass, separate R and then recycle the unused reactant A. So, it would help to maximize the intermediate product or the desired product. Now, let us consider first order reaction followed by zero order reaction. So, for a typical case of A to R to S, this is K1, this is K2, and this is first one is first order, N1 say it is 1 and N2 is 0. So, rate of reaction minus RA would be K1 CA, RR would be equal to K1 CA minus K2. So, here capital K is the K2 by CA naught by K1. If we define so, and if we start with CR naught is equal to CS naught is equal to 0, no R and S present. In that case, we can, the first one would be concentration profile, we can derive CA by CA naught would be equal to e to the power minus K1 tau or K1 T, and for the second reaction we can write CR by CA naught is equal to 1 minus e to the power minus K1 T minus K2 by CA naught T. So, the maximization of CR can be obtained by differentiating and setting it to 0, the CR equation. Then we can write CR max by CA naught would be equal to 1 minus K into 1 minus ln K, where K is given as K2 CA naught by K2 by CA naught divided by K1, and T max can be obtained as 1 by K1 ln 1 by K. The concentration profile, if we plot concentration versus time, for this zero order, a first order followed by the zero order reaction, we can get the concentration of A, that is CA naught, will drop, then concentration of R will increase, so this is for maximum, this is CR max, and this is the TR max. Then the concentration of S, which is zero order reactions, it will vary like this and become constant. So, this is S. So, this is for series reactions A to R to S, K1, K2 and N1 is equal to 1, N2 is equal to 0. Now, let us consider batch or plug flow reactor where zero order followed by first order reaction. So, the reaction is like this: A to R to S, K1 and K2, N1 is 0 and N2 is 1. So, rate of reaction, first one is minus RA is equal to K1, and second is formation of R is equal to K1 minus K2 into Cr when A is present, and it would be minus K2 Cr when A is absent. And K, capital K, is K2 by K1 by Ca0. With the same concept, Car0 is equal to Cs0 is equal to 0, and if we start integrating the red equation, first one, it would give Ca by Ca0 is equal to 1 minus K1 T by Ca0. Now, Cr by Ca0, this would be equal to 1 by capital K into 1 minus e to the power minus K2T for T less than Ca0 by K1, and this would be 1 by K e to the power K minus K2T minus e to the power minus K2T. This is for T greater than Ca0 by K1. Now, the maximum concentration of Cr can be obtained by differentiating and setting it to 0, that is intermediate. So, Cr max would be equal to 1 minus e to the power minus K divided by K, and T max or Tr max would be equal to Ca0 by K1. Now, if we look into the concentration profile, so this is concentration, this is time. So, the concentration of A, that is Ca0, it falls sharply to a 0 value, where at this time the concentration of R would be maximum. So, this is the concentration of R, then R will drop like this. The concentration of S would slowly increase and it reaches like this. So, this is for S, this is for R, this is for A. So, slope of this line is initial slope is equal to minus K1 and initial slope for this is also K1 . This is CR max and this would be TR max. So, this is how the concentration profile of different component in a series reaction can change from different order of the reaction. So, thank you very much for attending this lecture, and we will continue our discussion on reactor design in the next lecture.